Hi, this is Ronald Resquer, a BSE Ed Mathematics 3 student of the Mindoro State University Bungabong campus. What I'm going to report is one of the topics in Abstract Algebra under Ma'am Hazel Pauline Reyamosha. The topic assigned to me is all about the chapter 11, which is the fundamental theorem of finite abelian group. Okay, so we will be digging deeper what is all about this fundamental theorem of a finite abelian group. We already know what is group, and that is a set of things that you can combine in a certain way and that follows four basic rules. And these rules are the closure property, associative property or associativity, identity element, and the inverse element. These four rules have been tackled already, and if you wanted to look back and review, then you can do so. And so we will continue with our topic, the fundamental theorem of the finite abelian group. Now, in the finite abelian group, it says there that the abelian group, or the group that we will be talking about, is limited or bounded, that we are only going to tackle about bounded or finite groups, which is the abelian group, which follows so instead of just four properties, it adds the commutative property. Okay, now I believe you already know about the 5 rules that you need to follow in order for you to have an abelian group. Okay, so let's dig deeper with this theorem, as this theorem says that every finite abelian group is a direct product of acyclic groups of prime power order. Moreover, the number of items in the product and the orders of these cyclic groups are uniquely determined by the group. So let's first broken it down into 2, so in order for us to have a clearer understanding. First, it says on this first part, every finite abelian group is a direct product of acyclic groups of prime power order. So it only says that if you need to broken down a group into smaller groups, then it can be expressed by acyclic groups of prime power order. Okay, so let's have this example. For a number, let's say it's 360. 360 can be expressed as a product of 8, 9, and 5. But as it says by the theorem in chapter 11, it says that every finite abelian group is a direct product of cyclic groups of prime power number. Now, what are the groups that can be used in order to produce 8? So, with 8, we can express it as a power of prime numbers. So, if we are going to group 8 as itself, 4 and 2, 2, 2, and 2. So, there are 3 ways to express, again, this group of 8. Okay. Now, for the group of 9, so we can have or we can express it as itself a group of 9, and then a group of 3 times a group of 3. Or as you can see, these are the prime numbers at the bottom. So 2, 2, and 2, and then 3 and 3. So these are what we need. A product, or can be expressed as a product of cyclic groups of prime numbers. Now in 5 we only have itself. So we only have 5 itself. Okay, so these are some of the ways that we can express this number. So let's have, okay, so the number of items in the product and the orders of the cyclic groups are uniquely determined by the group. This is the simple explanation of it. In 2 to the third, there are 3 uniquely determined groups. So 2 to the third, it has only 3. Okay. 3 groups, or 3 ways on how you can express it, which are, okay, so the first way is z to the 8, and then z sub 4 times z sub 2, and this, as you can see, it is aligned to the power itself, uniquely determined by the group by means of its power. So there are 3 ways that you can group them into. Now with 3 square, of course, there are only 2 ways on how you can group them. So these are z to the 9 and z cubed and z cubed. And then lastly, with 5, it has only 1 way on how you can group it, simply because it's already a prime number. So that is with z sub 5. That is the meaning of the second part of the theorem. Again, okay, so let's have another example. Let's have this number 100. So in 100, we have this 2 square times 5 square, because if we are going to express it into prime power order, the prime number is 2, which is equivalent to 4 times 5 square, which is equivalent to 25, which is 4 times 25. And following the theorem, we only have 2 ways on how we can have a group of this 2 to the square. 2 square, we have z sub 4, okay, because it's 4 when we multiply it, and then we multiply it with z sub 25, so that is for the 25. And then if we're going to break it down into a group, we have z sub 2 times c sub 2. Okay, so this is what this means. Okay, so the power order, we only have 2 ways. Okay, so z sub 4 and z sub 2. In 5 square, we also have 2. Okay, so that is z sub 5 and c sub 5. So that is what the fundamental theorem of finite abelian group states. Thank you and have a great day.